Okay, we're recording. Off we go. So last time we were talking about path independence, and we made some observations about it. Drew some pictures. So I want to point out that it is going to end up being more useful conceptually than computationally, and here's why. And I don't mean to downplay the idea of path independence, but here's the thing: if it's path independent and you're going to use that for a computation, well, the thing is, if it's path independent, that means that it's also a gradient, as we previously noted. If it's a gradient, well, that means that you can use the fundamental theorem of line integrals, which is already awesome, right? So basically, path independence from a computational standpoint is a nice tool that addresses circumstances for which we already have an even nicer tool. Arguably, right? I mean, so there is a point of view that says you don't really need, from a computational standpoint, path independence doesn't really bias anything we didn't already have. So nevertheless, there are some circumstances where you can use it. Now, whether this is the best way to solve this problem is an academic question, but I want to show you that you can use it to solve a problem. So here's a vector field. I'm going to assert without evidence that this is path independent. You'll see why in a few minutes and how I know. But claiming that it's path independent, and we want to compute a certain line integral, in particular a line integral across this curve right there. Okay, so how am I going to compute this line integral? Well, from the fact that my vector field is path independent, the mere fact of path independence means that that if I tie down my starting point and my ending point and don't move those, I can move the path, change the path kind of however I want. It doesn't matter. I don't have to do anything sort of nice and controlled like that. I can also use that path if I want. Right? Of course, I obviously don't want to. But you can change the path to any path you like. It doesn't make any difference to the value of the line integral. That's what path independence tells you, right? So just because of knowing the path independence, I can say Fooey on the given curve. I'm going to use, I shouldn't have done that in green. I'm going to say Fooey on that given curve. Not going to look at that anymore. We're going to look at this new curve. Same start, same end. Again, that's a big deal. And I'm just going to compute the line integral over that second curve instead of the first curve. That I don't like because this blue curve here, if I parameterize that, it's going to be sines and cosines, and I don't want to deal with trig integrals and substitutions and stuff. It seems annoying. So that's a neat fact, right? From a computational standpoint, then I can just change the question pretty dramatically seeming. Waving the magic wand of path independence. Now, there are some nice things that happen here. You'll notice that this new curve, C2, it's easy to parameterize. After all, it's staying right here on the x-axis. Y is always 0, and x just needed to increase from -1 to 1. So, boom, right? Easy to parameterize. Thing about it is, the fact that y is always 0 means that I can plug in y equals 0 in the evaluation of the integral everywhere y shows up, because it is, after all, on this path, y is entirely 0. And that makes this term turn into 0, and that makes the dot product, right? That makes f dot dx just turn into flat 0, and we are done here. Right? And so we evaluated this line. Path independence was the first tool that we used, the main sort of like thing that allowed us to do this. It allowed us to turn a hard problem into an easy problem. And then, neat observation. By the way, this kind of geometric observation where, when you choose a nice curve, anything geometric about the curve, that's information that you get to plug into your equations. This is a really good tool. Be on the lookout for that. Try to find opportunities to use this if you can. But again, most of the credit here goes to path independence. How we doing? Everybody with me? Yes, question.
Could you remind us how you know functions path?
I did not tell you. Yeah, and that's I sort of apologized at the start of this that I'll tell you later how I knew that it was path independent. Yeah, coming up in just a moment. Yeah. All right. Okay, so in fact, here that is. So yeah, we've already seen that path independence and being a gradient, and then this sort of alternative point of view on path independence, these are all simultaneous, right? Any vector field, and again, we're ignoring regularity issues, and let's not worry about what's differentiable and what's only, continuous and what's furthermore continuously different. Wait, that's not what this class is about, so I'm going to sweep all that under the rug. For sufficiently nice vector fields, being a gradient is the same as being path independent, which is the same as saying that all your closed line integrals are zero. These are all the same concept. That we discussed all of those last time. So here's the thing. A closed line integral, if you look at this, we already have a word for closed line integrals. It's circulation. Right? We already have theorems about closed line integrals. In particular, one of our big theorems is Green's theorem that says that a closed line integral can be computed by a double integral of Green's operator over whatever interior is bounded by that closed curve. Right? So we can push these equivalent conditions, being a gradient, being path independent. We can push that forward a little bit by saying, also true then. I mean, if all the closed line integrals are equal to zero, well, that means by Green's theorem that all these double integrals of Green's operator are equal to zero. And this allows us to then do another realization, which is to say, wait a minute, all of these double integrals always zero? How could that be? What integrand have we ever heard of that has the feature that all of its double integrals for every domain are always zero? Zero. That's the only one, right? If it's non-zero somewhere, then any integral where it's non-zero, the integral won't be zero. So we immediately conclude from the fact that the integrals are always zero that the integrand must also always be zero. Okay, so now let me sort of point out then that if I connect the dots like that, then the nice conclusion and what we're going to really think of as being the theorem here is this right here. The state of being a gradient of something is simultaneous, regularity is used aside, simultaneous with Green's operator always being zero. And so this is what I like to call the local test. I call it a local test because it is something that you compute locally, right? You compute the value of Green's operator at a point. You have to check all the points, right? I mean, the formula for Green's operator has to be flat zero. But because of something that you compute locally, you can draw this conclusion that as a whole, this vector field must be, as a whole, the gradient of a single special, anti-gradient function. So that's a neat fact. That's how I knew, by the way, that this vector field was path independent, because I just at a glance can compute Green's operator, right? X partial of that is 2x. Y partial of this is 2x. They subtract to zero. That means that the local test is passed. This Green's operator is always zero. That means it's a gradient. That means it's path independent. Everybody happy? All right, so it's a really neat fact. Here's a streamlining, by the way, of this. I like this point of view. Keep in mind, this is a circulation. Right, we talked about that. This closed line interval, that's circulation. Just as an intuitive pitch. Let's not worry about the equations and the you're connecting the dots literally. But if circulations are always zero, doesn't that kind of make it sound like circulation density ought to be zero? Right? I mean, I think that's very satisfying. And if you want to make the connection in your mind, sort of intuitively that way, that all the circulations are zero, well, circulation density is zero. It just rolls off the tongue really nicely in that way. So that's another point of view. All right, last thing, real quick notational point. Keep in mind what Green's operator measures. Right, Green's operator measures the extent to which the vector field has a kind of the rotational aspect to it, that the fluid is that the little leaves that are floating on the creek are going to be spinning in some sense as they go downstream. So Green's operator measures how much of a rotational feature, aspect, characteristic the vector field has. And so if it's equal to zero, wouldn't irrotational kind of make sense as a term? So this is a common term to describe Green's operator being zero. And I like it because it's very descriptive and it's literal. It says exactly what it means. Okay. All right. Now, there is a lot of terminology to keep track of here then. So let me write some of this down. These vector fields that have this property, on the one hand, we've called them gradients. On the other hand, we've called them conservative. And now I'm throwing in an additional term, irrotational. Right? And I forgot, and we've also, of course, previously called them path independent. So that's a lot of terms. Right? And they're all talking about the exact same vector fields. They're different properties of the exact same vector fields, but it remains. They're talking about the exact same vector fields. So I find this a little bit frustrating. It's just, it's getting out of hand. How many words do we need to talk about these same ones? I'll tell you sort of, where I come at this situation. I like the term path independent because it describes an important property. And it, again, it says exactly what it means. It's the value of line integrals is independent of which path you pick. I think that makes a lot of sense. Gradient makes a lot of sense. I mean, that's literally, it's saying exactly what it means. And irrotational, right? Says exactly what it means. I pointed that. So these three I like. They're talking about, and sound like they're just verbally exactly talking about important properties of these special vector fields that we're just talking about. And so, with that noted, I asked the question: do we really need this conservative? Do we need that term? Is that helping us? I think it's just personally. I think it's creating confusion. Rather describe something as being a gradient instead of saying, I'm going to use the word conservative to describe it being a gradient. How about we call it gradient if it's a gradient? It just seems more obvious to me. So that said, a lot of books actually prefer to use this word, the one that's kind of the least intuitively satisfying of, why should we use it? So anyway, heads up, be aware you're going to hear that word conservative. What it means is a vector field that is a gradient, aka which is path independent, aka which is irrotation. All right. Yes?
We kind of think of the Green's operator as a cross product. Does this kind of go back to the cross product of the gradient is always zero?
Cross product of you're talking about curl.
Oh yeah, sorry, curl.
Yeah. There is a connection there. Roughly speaking, the point is that Green's operator is very closely connected to the curl operator that we talked about in Chapter 3. In fact, it's so closely connected, a lot of people, and I think I wrote this down somewhere previously, will actually write this as curl. Right? And so, there's a strong connection there. I don't, for personal reasons, highly subjective, I like to call it something different from curl. But yeah, you can in fact just call it curl. Yep. All right. Now, everything that we did up here is two-dimensional. This is all in R2. Vector fields, Green's operator is only defined if you're talking about a vector field that's in R2. So let's ask the question now, is there a three-dimensional version of this? Is there a local test for something being a gradient if we're in 3 dimensions instead of 2? And yeah, absolutely there is. And here's what that test is. The local test is curl being 0. Tells you that the vector field is a gradient. Now, why don't I have the demonstration of that here? Well, it uses a theorem we haven't covered yet. So I'm going to say this, that the way that we're going to demonstrate this fact is going to be highly, highly analogous to the way that we just got through demonstrating this fact, namely by way of using a big theorem. It's just that the big theorem we'll use down here we don't have yet. Okay. So that said, I'm going to go ahead and still use the theorem. So here is a vector field, and let's ask the question: is this? You'll notice 3-dimensional vector field. Is that a gradient? Be nice to know if it's a gradient. Should I bother trying to find the anti-gradient? Or is that a wild goose chase? Right. Okay, so I'm going to use the above theorem. The above theorem says if you're in 3 dimensions, and if you want to know if you've got a gradient, well, the way you resolve that is ask, well, is the curl equal to 0? So I'm just going to compute the curl and see if it's 0. And that's really easy to do. Let's start off by computing the curl, and here it is. And notice I didn't even finish the calculation, right? I computed the first component of the curl here just by taking the appropriate partials. And right off the bat, now I don't know the curl yet, but I know that I don't actually need to know the curl. I just need to know, is it the 0 vector? And I can already see it's not. Right, this first component, it's not 0. Certainly not as for all values of x, y, and z. It just isn't. Look at the formula; it's not always 0. So if the first component is sometimes non-zero, well, then the vector is sometimes non-zero, and so this condition here is not satisfied, and therefore my vector field is not a curl. So. Gradient, no. Everybody with me? All right. Okay. Here's another example. Now here's a 2-dimensional example. Looking at what I've got right here. Is this vector field a gradient? Now you'll notice, being 2-dimensional, I've got to apply Green's operator. And so I apply Green's operator, compute the appropriate partials. I get 2, which is not 0. So again, no, this is not a gradient. Everybody happy with that? Okay. Now in this case, I'm going to call this a satisfying result because we can draw a picture of this vector field. That vector field looks like that. Right? And so let's just take a geometric point of view on this. Okay, here's our vector field. Is this a gradient? From a geometric point of view, I think there is a very easy persuasive case to be made. Keep in mind, gradients point uphill. Right? So could this vector field represent uphill? No, it just can't, because I can't start at a point like this one and go uphill and keep going uphill and keep going up and up and up and up and up and get right back to where I was in the first place? No, that's not how uphill works. It just can't. Right? This is an Escher stairs sort of contradiction of nonsense. Does that make sense to everybody? Yeah. Okay. All right. So one way you can think about this idea, and I think this is satisfying, is keeping in mind that gradient points uphill, right? And we're talking about Green's operator, aka circulation density, So we're thinking about, and that's why I did an example here where I drew a circulation, right? Uphill can't circulate. Right? That's the observation I made here. If I start there, going uphill, doing a lot of uphill cannot add up to not having gone uphill at all. Right? So uphill can't circulate. So that's one way to think about it. Possibly you like. Doesn't matter. Okay, so we've talked about a bunch of ideas in 2 dimensions at this point. And in R2, bunch of ideas. I want to try to put them in order, in a sense, in an organized order, a usefully organized order. And so I have what I like to call the strategic diagram for R2. I want to first tell you where I got this from. You may recall I've mentioned previously that there is a more sophisticated point of view on all of this that we just can't talk about here. It's too much. Differential forms and chain complexes and cochain complexes, just more sophisticated than what we can do in this class. That said, what I've done here is to take a lot of the big, heavy machinery from that sophisticated point of view, kind of boiled out all of the sophistication and rigor. Right? And this is the bones of what's left over. So this is not something I kind of pulled out of thin air. This comes from importantly, meaningfully natural organization of the ideas. So here's let me walk you through what this does for us. So you'll recognize, of course, we have our gradient operator here. Gradients take functions and create vector fields. And Green's operator takes vector fields and creates functions. And this is what we've previously referred to as an exact sequence. Recall exact means that everything has a lifetime of 2. Right? And we've already talked about how that's a nice thing to know, because if you have something and you compute its gradient and it gives you a non-zero vector field, well, guess what? Green's operator's got to be 0 because it's had its full lifetime of 2, and so it dies. Okay. And analogously, if you have a vector field and you compute Green's operator and you get 0, okay, well, that lifetime of 2, that means that there must be some function over here, right? There's got to be a function whose gradient gives you that vector field. If there weren't, right, if there were no such function, and if this were the lifetime, that's not a lifetime of 2. Right? So it is not possible for this to not exist. So anyway, that's, again, my little lifetime metaphor, and I find that satisfying. Okay. Here's the thing. You can do something similar with points and curves and 2-dimensional regions by thinking about how they're related by way of boundaries. Right? If you have a 2-dimensional region and you take its boundary, you get a curve. And now, side note, if you have a curve and you take its boundary, then you get, well, a pair of points. Right? And I claim this too is a kind of an exact sequence. We haven't really talked that through yet, but I think it's a neat observation if you think about it. If you have a curve whose boundary is 0, well, wait a second, well, a curve doesn't a curve sort of start and then end, and then wouldn't the boundary always be a pair of points? Well, not if the curve starts and then ends at exactly the same point. And if that happens, right, if there is no boundary because it starts and ends at the same point, notice that yes, there is indeed a region whose boundary is that curve. And vice versa, too. If you have a 2-dimensional region, and you ask, okay, what's the boundary of my 2-dimensional region? Well, the boundary of your 2-dimensional region is a curve. Sure, it's a curve, but it's a curve that has to start and end at the same point because it's a boundary, and that means that its its boundary must be 0. So I think that's kind of a neat fact. So we have kind of two exact sequences here. Now let me talk through the theorems that we've seen before. We've talked about the fundamental theorem of line integrals. That says that if you have a function and you evaluate it at a pair of points, endpoints to a curve, that is, in this way, namely you compute f at the endpoint minus f at the starting point, namely if you compute this thing called change. That tells you what you get when you take the vector field and compute the line integral over the original curve. Right? So, in some sense, these operators here, taking a gradient and taking a boundary, make the left side equal to the right side. Now that's just a restatement of the fundamental theorem of line integrals. Now let's do it over here, one notch over, where we take Green's operator and then boundary. And let's see, what does Green's theorem say? Green's theorem says that if you do the circulation around a boundary curve of a vector field, keep in mind, it says right here, this curve is a boundary. Right? Then that gives you the same thing as the double integral over the anti-boundary region of Green's operator. So it's a really neat sort of diagrammatic sort of chase. It looks like a coincidence even, right? That this equals that, and this equals that, when you set up the operators in this very special certain way. Okay, so I think that's a neat thing. To lay a little bit of groundwork for the future, I'm going to draw a little bit more pictures on this diagram. There's some special vector fields that we've talked about, kind of, again, sort of summarizing what we've been doing recently. There's some special vector fields. These are the ones that have all the names that we just discussed. So one feature of our special vector fields is that they are gradients of some function. Each one of these special vector fields is a gradient. We've also talked about how each one of these special vector fields, Green's operator is 0. And we've also talked about how these special vector fields are path independent. Namely, if you have any two curves with the same exact boundary points, then you get the same value of the line integral. So these properties, I kind of like to draw. I don't know, maybe it's just because I'm a visual thinker or something, but I like to have a visual representation of what they look like on the diagram here. Also, quick reminder, how did we make the connection that between the green property and the orange property, right? How did we connect path independence to the state of being a gradient? Well, we used the fundamental theorem of line... Oh, wrong color choice. I can't do that. We used the fundamental theorem of line integrals to connect the green property to the orange property. How did we connect path independence to Green's operator being 0? We did that just a few minutes ago. We did that with Green's theorem. So this layout, I think, has value in that it you can kind of see how the pieces fit together, and that everything kind of fits together in a reasonably natural way. Just so you know, a little bit of a preview, we're going to have a three-dimensional version of this diagram. We don't have the theorems yet to fill it in, but there will be a three-dimensional version, and this picture, practically exactly as written here, is still going to work. Yeah, you had it.
So on the left side, it's equal to the non-change. That's what the little triangle is. So then it's the little like the same.
Yeah. That's right. This represents change per that formula. Yep.
Okay, and then on the right side, the real sigma.
Yeah, this is lowercase sigma as a typical choice for describing circulation. Yeah, exactly. All right. So last observation I'm going to make is about computations. So sometimes you can use these theorems to compute stuff. So for example, suppose you want to compute a line integral. And again, there's going to be a three-dimensional version of what I'm showing you here as well. All right. Well, where are the line integrals in this picture? Well, here's the line integrals. And so if I want to know, hey, can I use this theorem right here? The diagram kind of shows you what would need to be the case for that to work, and also how you would test whether it is indeed the case. Can I use the fundamental theorem of line integrals? Well, I would need for my integrand to be a gradient of a function. Or said differently, I would need to be able to take my integrand, I would need to be able to find an anti-gradient. Now, so notice, in other words, I have to be able to take the vector field I have, I need to move backwards through the gradient arrow, as it were. I need to take the output of gradient and reverse engineer how to find, is there an anti-gradient? Okay. Next question, how do I decide if there's an anti-gradient? Well, I take Green's operator and I see if I get 0. Right? And the diagram kind of, it's just right there. I mean, I can see I need for this theorem to work, I need for that arrangement to be the case, and this business connects to this business by way of exactness, aka likeness. Is everybody with me? Okay. All right. Next question: Can I use Green's theorem? So, another possibility if I want to compute a line integral. Well, maybe I could use Green's theorem. How do I decide if I can use, let me do it like this. How do I decide if I can use Green's theorem? Well, on the vector field front, there's really no issue. Whatever my vector field is, I'd need to compute Green's operator of it. That's not an issue. You can always compute Green's operator. It's a bunch of partial derivatives. You just do it, right? The question, though, is I would need for my curve, that would need to be a boundary of some region. Right? That's, again, right there in the statement of the theorem, my curve's got to be a boundary. Said differently, and I like this lingo, I've never heard this anywhere else, but I think this is really nice. I would need to be able to take the given curve and move backwards through the boundary arrow. I would need to know, is there an anti-boundary? Right? I think that makes sense. How do we decide if there's an anti-boundary? Well, you play the same game as usual. You decide if there's an anti-boundary by seeing, use exactness and take the boundary of what you have and see if it's 0 or not. Usually this one's geometrically kind of more self-evident. You have a curve. You want to know if it bounds a region. You got to see if it closes up. Are the endpoints the same or are they not the same? But from a diagrammatic standpoint, again, the diagram kind of points you toward that idea. Okay. All right. So, hope that'll be useful. And now we come to the question that's been looming over our heads this whole time. How do we find these anti-gradients, right? There's been a couple of examples we've done so far where I've just kind of produced an anti-gradient. Just like, yeah, there you go. There's our anti-gradient. Right? How does one do that in practice if you don't just, if you can't just look at it and see it? So here's the idea. If I have a vector field and I want to know, is that vector field a gradient? Well, a vector field has components. If it's a gradient, this is what a gradient is. And so the question of whether the vector field is a gradient boils down to the question of, can I find a function for which P is the F partial and Q is the Y partial, and R is the z partial, right? This is what I've got to do. I need to know that there is a function f that makes these two vectors the same, aka I need a function f that makes these three equations true. And now I'm going to look at these three equations and point out that I can rewrite each one of them. So for example, saying that P is the x partial of f, well, that's synonymous with saying that f is the x antipartial of P. Same statement. Is that cool? And then minor little note, don't forget that when you talk about antiderivatives, you always have to say plus c. Keep in mind further, the reason we have to say plus c is because when I take the x partial of this equation over here to produce this equation over here, any constant that was over here, of course, is just going to disappear when you take that derivative. But the thing is, here I'm taking an x partial. So not only will constants disappear, but any function that doesn't have x's in it. And so any function of y and z will also just disappear when you take the x part. Right? So you don't technically need f to be a specific, particular x antipartial. It could be any x antipartial. And then likewise for the other equations, the y partial of f equaling q would mean that f is the y antipartial of q. And again, with the constants. By the way, these functions here are called partial constants because they're partial derivatives, or they behave like constants with respect to a particular partial derivative. Okay, so what we have then is some algebra that you can write down. You write down this algebra and you play the game and you just ask the question, can I find such an f? And I like to view it as kind of a little puzzle, like a little jigsaw kind of a thing. And so let me show you how this puzzle plays out. Here is an example. Let's find an antigradient for this vector field. And now, by the way, you want to make sure you don't go on a wild goose chase. Right? Don't try to find something that doesn't exist. If your vector field is not a gradient, don't try to find an antigradient. It's not there. So how do I know that the antigradient even exists? Well, because if I take this vector field and if I compute curl, and that's a little bit of algebra, and you can just do that if you'd like. You do get 0, and so there should be an antigradient to find. Okay. All right. So here we go. First coordinate. I've got to take the x antipartial of that first coordinate, and then the second coordinate. I've got to take the y antipartial of that second coordinate. And then likewise for the third coordinate, I've got to take the z antipartial of that third coordinate. Just playing this game that we have up here. So we write that down. Let's compute these antipartials. These are no big deal, right? The x antipartial of that. Easy little antipartials, nothing to it. Likewise the others. Don't forget to add in your partial constants. Right? Very important to add in those partial constants. Notice, if I were to ask the question, hey, are these three things here all equal? They absolutely are not. Right? But again, this is the mistake. You don't need I don't need to know that that a specific x antipartial of P is equal to a specific y antipartial of Q, etc. I need to know that there is an antipartial of P that equals also to an antipartial of Q that equals to an antipartial of R also. And so again, these partial constants are the necessary tool there. Okay, so let's try to construct such an antipartial. Let's try to find an f that's simultaneously equal to all three of these things. And I argue as follows. I see x squared y there. I see x squared y there. Kind of feel like there's going to have to be an x squared y term in my answer, but there isn't one here, right? And that's depressing and discouraging right up to the point where I realize, wait a minute, this could be any function of x and y over here. So how about I just say, all right, I'm going to let C3 be x squared y, and then indeed there is an x squared y in all three of these terms, in all three of these expressions. So I made that pair up. Is everybody on board? Okay, and then likewise, I see an xz, I see an xz. There's not one here, but oh, hey, maybe this is xz. Perfectly allowed. That is a function of only x and z. No y's in there. So, cool. No problem. And then likewise, I got a minus yz squared there, and hey, I guess that's what this could be. And so everybody wins, right? This worked. That is equal to this is equal to this is my antigradient. So I've found the antigradient. That's how you do it. By the way, of course, obviously, this process will not work if there is no antigradient. So easy example of that sort of a failure. Now, we've already seen that this vector field, Green's operator is not 0. There should not be an antigradient here. This is not a gradient of anything. Right? This is a circulating vector field. It can't be a gradient. So what would happen if we tried to find the antigradient that we know does not exist? Well, first coordinate, take an x antipartial. Second coordinate, we take a y antipartial, and you take those antiderivatives. Don't forget your partial constants. And let's play this game. Can I find a function that's equal to both of these things? Right? What could these functions here possibly be that would make the top line equal to the bottom line? And we lose. This is a no-win game. Can't do it. Everybody see why this? You're painted into a corner here. You lose, right? Yes.
In the previous question, do you want us to have like a plus C in the answer? Like
Oh, I don't care.
Okay.
Yeah. I don't care. Vast majority of the time, you're going to need an antigradient anyway. That you don't need the general antigradient. You just need an antigradient, and so there's no need for a plus C anyway. Yeah. Right. Good question. I'm glad you asked the question. Yeah. Okay. All right. So yeah. So this is how you find the antigradient. This is how I found the antigradient to that first example that we did last time. Where we used the fundamental theorem of line integrals. I pulled out of thin air, right? No, I just did this process to find it. Okay, so we're done with chapter 6. Moving on now to chapter 7. For, what do we got here? 8 minutes? No, 6 minutes? Anyway. So we're going to do a bunch of analogous stuff now in 3 dimensions, right? We've done a lot of 2-dimensional stuff. Green's theorem is intrinsically 2-dimensional. Fundamental theorem of line integrals actually applies in 2 or 3 dimensions, but we've been mostly focusing on 2. So there are some very different, cosmetically different. There are some highly analogous but cosmetically different theorems in 3 dimensions that we need to develop, and they involve this thing called a surface integral, and we haven't really done surface integrals yet. So we're going to spend a certain amount of time here in chapter 7 just developing the idea of a surface integral. And in order to be able to do a surface integral, we have to define something called a parametric surface. So this is just a first step. Again, we've got to develop some machinery, and then we'll get into the big theorems. So a parametric surface is a lot like a parametric curve, right? A parametric curve is position as a function of a single parameter, right? Position is a function of time. That's the way we think about it most of the time. Right? Well, a parametric surface is just position as a function of 2 parameters instead of 1. That's all it is. And we've actually seen an example of this previously, so I like to start with this one. This is straight out of section 1.5. We talked about how to parameterize a plane. And the idea was that if you have a point in the plane, and if you have a couple of vectors, v1 and v2, that are parallel to the plane, right? Well, then, these 2 vectors define the directions. In some sense, these are the directions I'm allowed to move that will keep me in the plane. And so let's just look at everywhere I could possibly get to in that way by starting at your starting point, which, it's a vector, but I like to think of it as a point. You start at that starting point, and then you go by, let's see here, by some amount in the v1 direction. You'll note that's a scalar multiple of v1 if you're moving in the v1 direction. And then from there, also, you're going to go by some amount in the v2 direction. That's going to be a scalar multiple of v2. So if you start in the plane and then just move arbitrary different amounts, s and t, factors, however far you want to go in the v1 direction, however far you want to go in the v2 direction, that's going to kind of trace out the plane. Everybody see what I'm talking about there? So this construction, this idea of position as a function of 2 parameters, my 2 parameters here being s and t, right? Position as a function of 2 parameters will make in this case, a plane, and I say in general, it'll make a surface. Okay. All right. Now, the one little asterisk I got to put on this is, it's not exactly like a parametric curve. When you're doing parametric curves, you can think of your single parameter as being time. Right, and that's our very common sort of standard way to think about a parametric curve as position as a function of time. You imagine a movie in which you're tracing out that parametric curve. So you have to abandon that, right? Because if you have 2 parameters, right, they can't both be time. Right? It'd be a weird, again, super sci-fi, that's not a thing in the real world that we can, right? That just doesn't work. So abandon this idea of parameter being time, but it remains position is just a function of the parameters. Okay. All right, so what I'm going to show you now is a bunch of different ways to parameterize surfaces. The book has a bunch of examples of parametric surfaces as well. The problem with the book's point of view, my opinion, is that the book shows you a bunch of examples where they start with a parameterization. And then they infer from the parameterization that you're started with what the surface looks like. Most of the time we need the exact opposite of that. Most of the time it's like, well, we've got a surface here. I know what the surface looks like. What I need to know is what is the formula, what is that parameterization? Most of the time I need to, it's not that I'm going from an existing formula to a picture. Most of the time I have a picture and I would need to know what's the formula, what is the parameters, how do I parameterize this surface? So the book's examples are, again, all sort of in what I'm going to call kind of the wrong order. So I'm going to show you several examples of how to do what we really need, how to create parameterizations. So the first one is, you might even see this coming, it's the graph parameterization. We've already talked about a graph parameterization. If one variable is a function of the other, then we had this little deal that we did, boom, we parameterized a curve. Same thing here. If one variable is a function of the others, just let those 2 input variables be your parameters. That's the trick. Let the 2 input variables be the parameters. And then you notice then I kind of don't even really have a choice as to what the third variable is. Z then kind of has to be what the function says it is, and lo and behold, we are done. We have formulas giving position as functions of two parameters s and t. So this little strategy, I mean, again, very, very simple. Just works, no problem. It doesn't even have to be z that's a function of the others. Look what happens if you have y as a function of x and z. All right, so y is the function. X and z are the inputs, so I'm going to let x and z be my parameters. And then that forces me to choose y to be that. Right? I mean, we had to do a little bit of algebra here. I had to actually solve for y. Right? Y was not given as a function of x and z, but I can solve for it and make it a function of x and z. And then, boom, graph parameterization. And what's great about the graph parameterization is I don't even have to know what this surface looks like. Right? Just merely from the equation, I can create the parameterization. And I'm bound to be out of time. Oh, yeah, okay, definitely out of time here. Okay, drawing the line right there. Y'all have a good Wednesday. See you on Friday.